Welcome to the time series forecasting on Digital Hub webinar. In this webinar, we continue our analysis on the gas well time series data. Material presented here, including but not limited to text, images, and codes, are subject to Digital Hub terms and conditions and are for demonstration purposes only, and may include future product features and plans. Sharing, copying, reproducing, and modifying them in any form requires Integra's permission. Please utilize the Q&A section to ask your questions. If you have any questions regarding the webinars and our use cases or Integra and Digital Hub, you can ask them in the Q&A section. We will answer them during the webinar if the time allows. If not, we will encourage you to go to our Q&A group on Digital Hub community, that we will have more discussions over there. Next slide, please. So I'm Hodar Zai, I'm your host here. I have Babak Shafi, Integra's founder and CEO, with me, and Sylvia Lee, our data scientist. As part of this series, we will have an upcoming webinar on April 13th, which will be discussing Digital Hub best practices for data science. So please make sure that you register for this webinar as well. We will have the link on Eventbrite and also our LinkedIn page. I encourage you to join the Digital Hub to be able to access the notebook and the data that we're going to present here, and to follow along during the webinar. It's just 3 easiest steps. You have to register and create your account. You need to be subscribed to a plan that we are offering it for free for webinar attendees and also students. You can use the code OBHUB in the student section, student ID section, the promotion code section, to be able to access the plan for free. And then you need to create a project, and you can find the notebook and the data in the notebook templates in Digital Hub. And with that, I'm going to hand it over to you, Babak, for an introduction and overview of Digital Hub and Integra.
Just looking at some Google Analytics right now, I see people from UK, from US, from Canada, from Nigeria, from India. So good morning, good afternoon, and good evening, wherever you are in the world. This is quite exciting for us to see that a platform that we built, and we always say we build it with love, is getting traction, and there's so many good feedbacks. We're very excited about what is happening in this space, and we're having a lot of fun. I hope that you will join the platform and you will have as much fun as we do creating models and really putting AI and ML to practice. There's lots of academia or academic conversations around how to use it, but what we have found most useful is actually to get hands-on and to start to apply the techniques that exist today, and they're very well established, a few of which we will see today, into solving an actual problem of, for example, a declining gas well production, or understanding the potential future of the gas, or identifying a break in the in an asset. That is the real use. There's a lot of high-level talk, and what we need is more and more use cases in this space. And it's just going to come if everybody starts to pitch in. It's everybody is going to start coming. Most of you are rejoining these events, so I'll keep the introduction for Integra very short. We basically are a small boutique consulting firm who built Digital Hub, and we built it because initially we needed it for ourselves, and during COVID, we thought, okay, let's focus on building it up for everybody else. We're putting tons of investment to make it happen, and we are making it available pretty much for free for you to get it, to use it, and demonstrate that, hey, AI and ML has. A lot of you might be engineers or transitioning from your current role into a data science role, or you might be managers or might be a service provider to the industry that are looking to see how can I add value to my customers with additional services. And Digital Hub is going to make all of this a lot easier, and how it will do it is it will allow you to experiment. quickly at very low cost, experiment with ideas that you have, whatever side of business services, if you're in drilling, if you're fracking, if you're production optimization, if you're in construction, if you're in exploration, you could use the data you already have to understand how you can improve your services to your customers. So what Integra offers is obviously our expertise in oil and gas. So if you need a hand, please reach out. We're happy to help you share our experiences at large organizations where we have deployed these technologies. We are also offering the platform that can be used individually for free if you're attending these webinars and you're part of the community, or for a very small fee. And we also have a community where we share information, and it's across different channels. So we chat on LinkedIn. So if you're part of the chat rooms in LinkedIn, you will see the information we're sharing. If you're part of our actual community, you will see some information there. And obviously, we'll continue to engage in dialogues and share what we know. We obviously don't know everything. We know just probably just a small piece of the puzzle. But I think if everybody comes out and shares what they know, others will improve it and make this whole thing much better. Let's go to the next slide. Sylvia has some really exciting, techniques she's going to use. So I'm not going to take too much time, but I did want to mention what is Digital Hub, right? And we say it's ready for innovation. It's really important. I come from the corporate background. I've been in this business of data and analytics for 20 years, consulting with IBM, Deloitte, and then leading the largest oil and gas organization here in Calgary or in Canada. As a director who stood up the entire platform. So I understand what are the needs in the corporate. I also understand what are the innovation in the open source, and one of the gaps I wanted to fill, and I think I've filled it with this Digital Hub, is to bring all the innovation that is in the open source into hands of people who otherwise would not have access to it, or would not know how to configure or how to put it together. Digital Hub offers data visualization. So if you're a business user and you have some data, you want to create a dashboard and look at your historical data and look at some information, you can easily do that. It also has machine learning engine that does AutoML. And if you are a data scientist, you want to get a little bit more advanced, but you don't know how to actually do predictive models, use AutoML. And it has all the tools and package for data scientists like Sylvia, who can actually analyze the data and create models and produce reusable collateral for the organization, as well as it offers you governance. So it's something that we haven't talked about this much, but I think it's important from a corporate point of view. The Digital Hub gives you, if you wanted to have a central team to manage these projects, you could actually have someone who manages the projects, the teams, and the cost per project. So cost was very important. Coming from oil and gas, it's not the best times in the oil and gas. So we were very cost conscious. And we made this platform that literally would have cost millions of dollars just a few years ago in a way that you can, with a few thousand or a few hundred, you can actually develop a use case and you can actually demonstrate it to your end users. So if you have any questions about any of these areas, please do ask. But this governance I wanted to highlight today, and that's what we've done. If you go to the next slide, we also targeted specific people coming from the industry. We wanted subject matter experts to have access, same access to the same data that a data scientist is working on. And for a data scientist, data scientists are pretty savvy. They usually set up their own environment. They love kind of fiddling with codes and packages, and sometimes you take that away from them, that's half of their job. But in the corporate, I had a few of them, and it was a challenge. We wanted their time to be spent on developing models and analyzing the result of the model as opposed to configuring the packages. And that's what Digital Hub takes away, and enables the data scientists to really focus on and I would say average data scientists. A savvy data scientist probably knows what to do, but it's still Digital Hub gives you a platform to go in and share your data sources and share your notebooks and bring in team members. So it's beyond just an individual. And as a developer, if you have programming background and you're getting into data science, we want to enhance your software with AI ML, a very convenient place to do so. Next slide, please. So convenience, like you said, that was a good segue to this slide. So you can access everything through a cloud, through a browser. You log into your browser from any machine, and you will access the same data, same database, same interface. So it's very convenient. You don't have to install anything. You don't have to learn multiple different interfaces. It's scalable. So at the back end, we leverage the latest technologies and Kubernetes and Docker to kind of deploy the infrastructure that is required for a given project. And so it can highly be scalable. As a matter of fact, that also leads into the costing, and that's why it's very low cost. You technically, when you create a project, you turn on an infrastructure, and when you pause the project, you no longer pay for that project. So you can have 10 projects and they could all be paused, but when you need it, you can turn them on, and you only pay for it in using that project. The system works on an hourly basis. So if you use 20 hours, that's how much you pay. And each subscription level has certain hours. The teamwork is another level of sophistication in the platform. So you can invite other people to collaborate with you, use your resources. So if you have a, say, team subscription and you have 300, 200 hours, 500 hours, you can invite other people, and they don't actually have to be a subscriber. They could be any user just with an email. They will log in and they will use the same features that you are using. So it could be one individual. Let's say if you're a freelancer and you have a team of other people working for you, or you're an IT leader or IT administrator, and you have a number of other data scientists, they don't need to be signed up on Digital Hub. You can just create this account and then invite them. They will have to have an account, but they don't have to be a subscriber. And a central database is very important. So we wanted all the information that is created, through that data wrangling and data engineering, creating those pipelines to come into one place, which we have done in the Digital Hub. Next slide, please. I talked a little bit about this. We have some early pricing going on. Make sure you subscribe to a plan. The academia plan is for students, but anyone who also joins through these events or has the secret code, they can sign up for the student plan for free. That will give you 40 hours of compute. And if you need, the good thing about this plan is, although the base plan is free, if you want to add more hours, or if you want to add more storage, you can just buy them incrementally. So you're not committing to a monthly plan, but you can add, the hours that you need. So if 1 month you need more than 40 hours, great, just buy another 40 hours. And the hours are extremely cheap. We're trying to figure out how to communicate that. But it's in our FAQ. You can look at the FAQ for the details, but the hours are the prices for the hours are very low at this point. So take advantage, bring in your model, bring your data. And we've done this. We've also provided lots of templates to get you going. Next slide. With that, I'm going to leave this to Sylvia. She's got lots to show you. So take it away, Sylvia.
Thank you, Babak. So hello everyone. So then now we're actually gonna move on into the time series analysis portion of this demo. This will be a continuation of our last webinar where we started off on processing techniques on time series. So if you do want to do some review, we do have that webinar available on our YouTube channel that you can go back and look at, or the notebook is still available in the Jupyter template. So you can always go back to look at them. But today we're going to continue in terms of how to build a model for the time series. So now we're going to move on into what is time series stationarity. How do you build the ARIMA, which is very famous and popular modeling for time series, and then how to actually do the forecasting. So with that, I'm going to leave the PowerPoint and head into our Digital Hub platform. So you can quickly just go to Digital Hub by going into cloud.digitalhub.io. Can have a sign up here if you don't have an account with us. And now I'm just going to log in. So when I'm logged in here, what I will see first thing is, of course, all of the projects that I've created, and also the projects that other people have created that have shared with me. So this is the part where Babak was talking about the team's plan. So in this case, he had a team plan, he created the project, and he shared it with me. So when I go into this project and use it, it will actually be the resources on Babak's team subscription. And then so that's how you can generate that collaboration and teamwork going. I'm just going to quickly show you how we can quickly develop and create a project. A project is what we is the base unit in Digital Hub. So we mark all of our workflows here as like a project. In this case, I'm going to select a data exploration project that I'm going to go into. Next page, I will see is some components. In this case, we have two for business intelligence and time series visualization application here available to choose, and of course a Jupyter, which is going to be the main platform that we do most of our development work on. I have a Teams plan, so in this case, I can now add in different members that I want to be part of this project. So I might add a Hoda. I'm gonna select her to be an owner of this project. And then moving on forward. The last part is that I'm just going to give my project a good name. So in this case, say I am still doing more time series analysis on gas well data. A good description. I might give it a tag later on to help me find this project better. And just quickly through a few steps, now my project is now going and getting deployed on the back end. So when you go into the project here, you see that we're provisioning all of these components here. So what this is actually doing is that in the back end, we're generating a superset application deployment for you, a Grafana deployment for you, and a database, a centralized database that interlinks all of these components together for this project. So with different projects, even though you might have the same application, say I have superset as well in my other project that we've prepared for this demo. In this case, this one is Pulse. So these are two completely different atomic deployments to keep your project segregated and organized away from each other. So now we're actually going to go into the notebook here that I prepared. So I'm just going to launch my Jupyter Lab. And then we'll go through the notebook and see how we built this time series model. First thing that I will show you is that when you launch your notebook, you're going to see a template here. So this template is where we have stored all of the notebooks and template that we have well demoed and showcased in the past. So with machine learning, the last webinar where it was on time series processing, and in this case, we're going to do time series analysis, which is the second part here. So you'll be able to access this exact same notebook that I'm about to show you through this template section here. So now over here, what I want to also show you is these are just some folders that I have, but specifically in the project folder. So this project folder, these are actually projects that I have on my project settings there, and then according to what I have on my Digital Hub here, and also the project I'm part of. So then like what you will see in this case is that like these are actually directories that is shared among all of the team members. So if Hoda is also part of this project, she goes into her Jupyter Lab, goes into project, time series analysis, she'll see the exact same thing. So this is how, just one way that we facilitated teamwork and facilitated how we share information and I guess like work across to each other. So now I'm just gonna go quickly into my time series analysis notebook here. So I've already pre-read this notebook for time purposes. In this case, I'm just going to show you. My screen is okay. So then like what we have here for this notebook, just a continuation and a little bit of recap from last time, we have gas well production data. So on this gas well production data, what we're going to do is to look at the different trends because like knowing some of the historical performances and understanding how some operating metrics, it becomes very important in terms of how we make decisions about production and optimization. There are simulation tools out there to generate simulation for these reservoir because it is very complicated. A lot of different factors comes into play. But in general, these to use the access of these simulations, it's not available to everybody, data scientists, and it becomes very technical to work with. Whereas like if you have a historical data, it's generally available to everyone. And then so the purpose like for like from the last webinar to this one is to just show like how we can do some general simple analysis to generate insights out of these historical data. So as I said, if you want to look into more about like different processing techniques for time series, please refer to the template notebook or to the YouTube channel for our last webinar section. So in this case, I'm just going to go straight into the resampling section here. And I'm not too sure why my screen is so weird. Okay, so in this case here now, this is the data that we're going to look at. What we used to have is a minute frequency data that we have resampled into day frequencies for us to identify the general trend of a flow data here. So with the flow of the gas well, we see that this is segregated into two different parts, whereas before August here, we have a very generally stable trend going downward from our gas well. But after August, we have some very dramatic big impact events. These might have been maintenance, turnovers. So then like, but these are events that like, you might use it for another sort of analysis for abnormality or accessing the impacts. But for this case, to go on forward with our time series modeling, we're going to use the first part, the first interval here up to August in our time series data to move on forward with our model building. So because of time, I'm going to go through the rest of the session fairly fast, but like there are a lot of resources and a lot of explanations in here that we've put it that you can go in and take a deeper read for yourself. So in general, a time series, we say it's a decomposition of like three major components. A trend, which in this case from our well data, we have a general downward linear trend, seasonality, which is the cyclic patterns, and then the residuals, which is the underlying random, seemingly random patterns of a time series. So like for the decompositions of a time series, we can use a very general Python module that can quickly just decompose it. But there are a lot of configurations then that you might have to get an accurate decomposition. As in this case, we do see a general downward trend that has been decomposed out of our time series, but I'll be relatively conservative about this seasonality that is suggesting. But the most important part here is to look at the residuals, because now this is, I guess, the underlying seemingly random processes in your time series that actually becomes very important in terms of model building. This also brings us into the concept of stationarity. So time series stationarity is the concept where your time series, the data point that is generated, is not dependent on time itself. Now this sounds kind of confusing, but like a general case is that, say, if you take data for the month of January, and then you take data for the month of July, what you should see, if the time series is stationary, is that your distribution of the data should look relatively the same. You should have about the same mean and about the same standard deviation and variance. So that is what says a time series to be stationary. Now this becomes very important because just as like other statistical models, there are lots of assumptions. Most common assumptions is the assumption of normality and independence. So same with time series modeling, stationarity generally becomes an assumption in a lot of different time series models. So then like this is, that's why stationarity is a very important concept in time series. Don't have too much time to go into it too deeply, but we do have posted some referencing and some online resources that you can go in and read a little bit more about. So just quickly going through, these are some very general examples of time series. Just gonna get the spoiler here. In here, really only B here and G here is stationary. And why they're stationary, you can go in and read a little bit more. But in general, because these ones are where you will see that your mean is going to be relatively the same and your variance is also going to stay general over time. So in order to check whether time series stationary or not, there is a lot of different methods. We're introducing two different methods here, which is the rolling statistics. So just as I say, if you take a window throughout your series and calculates the statistic, like the averages and variance for it, you should see it's relatively constant over time. And also we've introduced a statistical test here for you to also determine that. So if you reject your null hypothesis, so a p-value is lower than your threshold, then your data is not stationary. So if I do both of these methods on our data here, we see a general downward trend of the mean, and then also a p-value of 0.6, which is a lot higher than our threshold of 0.05. So both of these is indicating that our series right now is not stationary. So how do we make it stationary? This is why we talked about decomposition. So in the very general case is that you just take away the trend and you take away the seasonality away from your time series. Whatever is left for you, that's generally your stationary part of your time series. A very common method that is used is called differencing. So this is just how we take a time point and we subtract its previous time point from it, and then generate a new series from that. So this kind of transforming is called differencing. In general, usually a differencing of just a lack of one would suffice. Sometimes you might have to go up to order 2, 3, but in general, in a lot of cases, just taking a difference of 1 usually does give you back a stationary series. So in this case, I took my time interval, did the differencing, throw it into rolling statistic, and also that statistical test, the Q-Fuller test. We have a p-value much lower than 0.05, and we have a very constant mean. So now this is suggesting to me now with a difference of 1, this is now my series is stationary. I've also included the code for some other transformation here. As commented out, in our case, we're not going to go through them because we already have our stationary series, but just for your reference, that this is just some sample that you can look at. So we only have 2 minutes left. So we're already like reaching almost the end here, but we haven't got to the modeling part. If you're available, thank you for joining us. But if you're available, we're going to stay a little bit and maybe briefly finish this modeling part here as well. So
can I just take a moment? There was a request to maximize your browser size. I was just waiting for an opportunity to let you know. If you could do that, that'd be great. Thank you.
I think my browser, I'm not too sure what's happening to my browser.
Okay.
It seems to be cutting off.
Carry on then.
Is this better?
It's good for me. It was just a comment from a viewer, so I wanted to pass it on.
Yeah. Thank you, Babak.
Yeah. There's also a question about sharing the notebook. I will. It is in Digital Hub. I will answer it online. Thank you, Sylvia. Carry on.
Yes. So the next important concept that goes into our ARIMA model is the autocorrelation and partial autocorrelations. So this, in the very simplest term, autocorrelations is just how your current time point is correlated with its previous time point, and it's the complete correlations. So then like how it correlates with, just say this is our day frequency data, so how it correlates to a day ago, 2 days ago, 3 days ago, is complete autocorrelations. Partial autocorrelations is a similar concept, but it's more specific in terms of that. Your correlation between your 2 different time points is just specifically those 2 different time points. So say like you're looking at the correlations between your current time points and 3 days ago, the influence of your time points from 1 day and 2 days ago, they don't go into your partial autocorrelations. So this is just a slight difference in terms of autocorrelation, correlation, partial autocorrelations. This becomes very important in terms of ARIMA modeling because this is pretty much what the AR, which is going to be an autoregressive model, and MA, the moving average model, how we determine the parameters on it. So if we just look at the autocorrelations for this time series that we haven't done the differencing on, we see that like the autocorrelations, it's very significant all the way through 20 legs, whereas the partial autocorrelations goes significance up to 1 leg. If we do it on the difference data, now our autocorrelations become a lot more different in terms of the significance is only up to 1 leg, and your partial autocorrelation, the significance is up to about 5 legs. So the significance leg here now it becomes how we develop our ARIMA modeling. So then like there is a term P for our autoregressive AR model, which is pretty much just the significance leg on our partial autocorrelation plot here, which is, in our case, we're gonna go with 5. And then with our MA modeling, it's going to be the significance leg on our ACF plot here, which is 1. So this is, in the simplest case, how we generate or how we go about trying out different parameters for a model. So if you want to read a little bit more about how ACF and PACF plot, and then how they also go into ARIMA modeling, more on the explanation and concept side of things, I've included the link to a very good blog post here by J.S. Salvi that goes into that a little bit more. They can take a good read into. But in our case here, we just now take our parameters, P equals 5, Q equals 1 for MA model. D is going to be 1. This is stand for differencing, so the amount of interval that you need to do, the order of it for you to get a stationary series out of it. Just did a quick comparison of here with when you just fit it with a autoregressive AR model, when you just fit it with moving average model, and then when you put all of them together into a ARIMA model. So we thus do see a residual square decreasing over these 3 models, and then so our ARIMA model does give us the lowest residual square. So the ARIMA model would be then like what, in our case for the demo here, what we're gonna go on forward with the forecasting. So we're just going to generally use the module predictions from this module, Python module that we've used. And once upon forecasting, we can see that it does give us back this general downward trend throughout this very high impact time, and then giving us this general forecast into the future. Do keep in mind, because we are extrapolating the data, as to further you forecast, your uncertainty is going to increase over time. But in this case, we do see a very general downward trend that is seemingly correct in terms of like how our gas well flow is going to trend over time. Now the next section here, so that's pretty much ARIMA modeling. In terms of how you determine the parameters of P's and Q's, looking at the partial autocorrelation and ACF, that's the most simplest form of method in terms of how we go about first to like start trying out different models. But there are, as technology is advancing now, there are algorithms out there that helps you do like grid search and like randomized grid search to help you look for the best parameters for your ARIMA model. We didn't go into it too much on this notebook, but like it is out there. It's just in terms of sometimes when choosing these parameters, a lot of times it comes with experience. I have heard from people that they talk about where this is almost a form of art, but in general, usually how you choose your model is the model that gives you the best results, but also the simplest model that gives you the best results. So you don't want to do too over complexity as well. This is very similar to machine learning, where you don't want your model to be too complex, where you get into the problem of overfitting as well. The next part of the notebook, we do have a very, this is kind of just our creativity going in, where we have included a little bit of simulations part of it. You can look into how we specifically did this simulation combined with our ARIMA forecasting modeling. But in general, what we did is that with every single forecasted point into the future, there is a associated distribution of it. So the probability of what is going to be the next point. So then like what we've done is kind of took rolling validation, or sometimes called walk forward validations, tweaked it a little bit, integrated a simulation portion to it, and then so it's pretty much goes through a forecast the next point, take a random point on the distribution, include it into your history, and then make the next forecast point, include it into history, make the next forecast point, so on and so forth. And then for us in the end to generate kind of simulating what your data could look like in the future in this point where like we had the hydrometric events. So in the case where like if we didn't have these hydrometric events, so then the green squiggly line here gives you back a just the simulated values, whereas like your blue line that stay constant here, that still gives you back the rolling predictions. That is very similar to what we have forecasted with just the ARIMA model. So this is just a little creativity on our part that we throw out there for any sort of discussions, feedback, to generate some thoughts. So that would then a very quick wrap up of the notebook. Seemingly going over time seems to be our tradition now, but I will pass it over to you, Babak, for any closing statement.
Thank you, Sylvia. The majority of everyone actually stayed on. Thank you for staying a bit longer. I know how busy everybody is. I want to thank you for taking the time, and I really would appreciate if everybody starts to use some of these techniques on a daily basis for, perhaps, the work that you're doing, and make sure that this AI and ML is demonstrated in terms of what it can do as opposed to what it is today. And that will go a long way for the whole industry and the whole community of data science, especially those who are actively working in oil and gas. So again, thank you all, and see you at the next event.